Good morning, everyone. My name is Zane Ballister, and thank you for attending the presentation of my thesis titled A Simplified Test for Pleasure Boat Stability. I'd like to begin by acknowledging those who have assisted me throughout the thesis process. First, I would like to thank my advisor, Professor Neil Gallagher, for his continued guidance and support, as his vast reservoir of knowledge and experience has been proven invaluable to this thesis. I would also like to thank my reader, Dean Werner, and my editor, Professor Harris, for their insightful comments and constructive critiques throughout the development of this thesis. Lastly, I would like to thank the Oak Cliff Sailing Center for allowing me to conduct my testing and scans on their vessel, the Iroquois. As indicated by the title of my thesis, the main objective is to develop a stability test for vessel owners to easily conduct to achieve accurate stability information for their vessel. Another objective is to improve upon the procedures of past theses. This is primarily accomplished through the acquisition of new equipment and rewriting certain aspects of the testing procedures. The final objective of this thesis is to expand upon the Salient constant database created by Hambleton and Reed in their 2023 thesis in order to further explore the links between hull characteristics and the Salient constant. Now I'll provide you with an outline of the rest of this presentation. I will begin with the background of the thesis, including the history behind it and the work done by past Webb theses. I will then discuss the theory behind the development of the simplified test and the testing procedures done. I will then have some discussion on the results of this and prior theses, and lastly, I will make recommendations for future work. Now onto the history surrounding this thesis. The Candy 1 was a powerboat that sank in July of 2012. Before it capsized, there were 27 passengers on board, which was far too many for a vessel of this size. At the moment of the capsizing, the passengers had overcrowded the flybridge, which compromised the vessel's stability, causing it to capsize when hit by a small wave from another vessel's wake. In the image on the right, the Candy 1 is pictured, on the right, being raised by the Nassau County Police Department after its capsizing. This accident is what inspired the original thesis by Daniel Turoff in 2015. Turoff was inspired by this accident as it demonstrated the need for stability information for recreational vessels, which to this day is not required by the Coast Guard. He established the concept of the simplified stability test as determining transverse GM through a sallying test. In 2022, David Oakers and Tony Marie Cassage continued his thesis and were first to incorporate a 3D scanner to develop the model of a vessel's geometry. Turoff had to take his measurements by hand, which was both time-consuming and inaccurate. In 2023, Mark Reed and George Hambleton had the most recent thesis in this chain of theses, and they began development on a database of whole data determined through all the past Webb theses, as well as their own, so that links between the hull characteristics and the Salient constant could be determined. Now, the first bit of theory in this thesis is transverse stability. Transverse stability is defined as a vessel's ability to return to its equilibrium position after being disturbed by an external force or moment. The metacentric height, or GM, is used as an estimate of a vessel's stability. GM is the distance between the center of gravity and a vessel's metacenter. The metacenter is the point about which the center of buoyancy rotates when a heeling moment is introduced. As GM signs are directly correlated to the righting arm, positive GM will indicate that a vessel has stability, and the greater the GM, the greater that stability. An inclining test is used to determine the GM of a vessel in its current loading condition. The test involves applying weight to a vessel and then shifting these weights transversely to measure changes in heel. This test requires certain equipment and can be complicated to conduct, so it is not suitable as a simple test for the average vessel owner seeking stability information for their vessel. However, an inclining test is useful for this thesis in order to determine an initial GM for use in calculating additional hull data, such as the Salient constant. In previous theses, this testing was done while dockside, but it was noticed that the dock lines and fenders would interfere with the test, especially in the later Salient test. Therefore, one of the major changes in testing procedures this thesis has made is changing the testing location. Testing is now to be done at mooring while in sheltered waters in order to best avoid any outside interference, such as those caused by dock lines or vessel wakes. A sallying test is used to determine the roll period of a vessel. It involves inducing roll motion on the vessel and recording the time between roll periods as the vessel returns to equilibrium. The Salient constant is a hull-specific constant that can be used to calculate GM with roll period. By using the initial GM found from the inclining test, Along with the roll period found from the saline test in the as-inclined condition, the saline constant can be calculated using the equation relating GM and roll period shown here in the bottom right. In order to calculate GM with the inclining test, the vessel's displacement must also be known. By inputting a 3D model of a vessel into the software General Hydrostatics, or GHS, with the as-inclined draft also input, the displacement can be determined, and then so too can the GM and saline constant, once roll period has been determined. Now, on to the testing procedures. The first procedure is the development of the whole geometry model, which again is needed to determine displacement. The first step is to take a laser scan of a vessel. This involves setting up a series of white spherical targets around the vessel and taking several scans from a variety of angles. This results in a point cloud, shown here in the top right, which is a mapping of points over the surface of a vessel. This point cloud is refined using the software Autodesk Recap and is then input into the software Rhino 7 to convert the point cloud into stations and produce a body plan. The body plan can then be imported into the software GHS along with the as-inclined draft to determine the vessel's displacement. The Iroquois can be shown here on the bottom right, modeled in GHS. Again, an inclining test is used to determine an initial GM for use in calculating the saline constant. The procedure of the inclining test begins with the setting up of measurement devices that are used to record changes in heel throughout the test. Once the setup is complete, the test begins by applying weights on centerline, which for this thesis are 30-gallon barrels of water. However, as mentioned previously, the testing is now conducted away from the dock, so a gas-powered pump was required to fill and empty these barrels while moored. The pump I selected is shown here in the image on the right. Once the weights are filled, they are shifted transversely at set distances, and the changes in heel angle are measured. GM can then be calculated using the weight added, the distance they were shifted, change in heel angle, and displacement. Now, here's the procedure of the saline test. This test is also intended to be done while moored in order to avoid the interference from dock lines and fenders that was present in the testing of past theses. Before the test begins, it is again important to ensure measuring devices are set up properly. For this thesis, an inertial measurement unit, or IMU, is used to record roll angle during the test. This IMU is a piece of newly acquired equipment intended to reduce error that was discovered in past Webb theses. Previous theses used a digital inclinometer to record a roll angle, but there was a problem discovered with this. The inclinometer had a sampling rate of 2 Hz, which was determined to be too low to reliably record the maximum roll angle during testing. This new IMU has a sampling rate of 128 Hz, which should be more than enough to ensure the maximum roll angle is recorded every time. Now, once the IMU is set up, the test begins by inducing roll by having the persons on board run back and forth transversely across the deck until roll angles of about 5 degrees are being achieved. Once sufficient roll is being achieved, the persons on board will then stop on centerline and record the time between each roll period as the vessel returns to equilibrium. With the discovered roll period in the GM from the inclining test, the saline constant can then be calculated. Once the saline constant is determined, the saline test is then redone in different loading conditions to put the determined saline constant to use and determine the GM of the vessel in these new loading conditions. Once a vessel's saline constant is determined, vessel owners can test their vessel stability through a simple saline test. The saline test will determine the roll period, and then the saline constant can be found or predicted from a database of saline constants. The equation shown again on the right can then be used to determine GM for whatever loading condition is desired. Unfortunately, the vessel I am testing, the Iroquois, has only been returned to the water very recently, so I have not yet had the opportunity to conduct my testing, but I will be doing so this Wednesday. I would, however, like to discuss some of the results of previous theses to best explain what I hope from my results. In the results of past theses, there is clear error present. On the right is a saline plot from Hamilton and Reed's thesis, which is visibly jagged and lacking data points. It is clearly erroneous, as the plot should see a decrease in maximum roll angle with each successive period, but there is a clear increase from the second period to the third. From this graph, one would see that the vessel's roll increased, which is impossible. As mentioned previously, a large source of this error is improper equipment, as Hamilton and Reed used the inclinometer that took measurements twice a second, which resulted in the max roll angle often not being recorded. The new IMU, which takes over 100 measurements a second, should ensure that the maximum roll angle is captured every time and should produce much smoother graphs. Hamilton and Reed were the first to develop a database of saline constants, and they used this database to explore potential links between Hall characteristics and the saline constant. Using the data of Thesis prior, as well as their own, Reed and Hamilton had a total of 6 vessels to use as data points. From these data points, they discovered 2 promising potential links. The first of these is saline constant versus beam. As you can see, the relation does appear to be mostly linear, and the trend line has an R-squared value of 0.82. The next is saline constant versus length times beam times draft. The trend here looks rather similar, but the trend line here has an R-squared value of 0.89. Once I have tested the Iroquois and determined its saline constant, I can add another data point to these plots and either further verify these prediction methods or prove them inaccurate. For future work, I would recommend continuing to expand the saline constant database by testing more unique Hall forms, as the more saline constants that are determined, the more refined the prediction method can become. Another possibility for future work could be to retest the vessels of past theses with the updated procedures to determine the level of error that has been reduced, as well as verifying the information in the database. Thank you for attending my presentation, and I would now like to invite Zach, Payne, and Evan back up to help answer any questions you all may have.